Alright, folks, so, just want to keep us up to date. We're here on the 27th. We just have a few more days of class left. We'll have a quiz, a reading quiz on the 4th. That's on Tuesday. And it will cover the entirety of the next chapter. So that's the Optics of the Eye chapter. It's a fun chapter, and we'll get started on that today. And then also, that will be our last quiz, our last reading quiz. I forget how many we've had. I think maybe we've had, that'll be our 7th or 8th quiz. 7th? Okay, yeah. And then our 4th exam, which we'll talk about that on the 4th of December, but our 4th exam is on the day of the final. It's not cumulative, it's just like our 4th exam, so covering the material we've covered since the last exam. And as I said, some of y'all came in a minute ago, but we can push our due date for the paper to the 6th. Okay? So it was due now, but I'll push it back to the 6th just to give you a little more wiggle room. Now it's 1,000 to 1,500 word paper. I don't really care about the format that you use. You do have to cite several references. And so just use the format that you're used to, NLA or APA or Turabian or whatever it is that you use. I don't really care, as long as it's clear to me. I do just want to warn you about your papers that we'll do turn it in. So if you plagiarize the paper, I will know about it. There's really, you can't get past turn it in. Honestly, when I read a paper, I know if it's been plagiarized or not. And that is a 0. So if that happens, it's a 0. And then also just, I want you to be aware that if you cut and paste large sections, and even though you might cite it, that's still not appropriate. That you should read your sources and then assimilate that material and then incorporate it into your paper, still citing it, okay, but not cutting and pasting. You might, quote small short segments, half a sentence or maybe even a full sentence, but plagiarism includes more than just taking somebody's paper off the internet. Cut and paste large sections, that's also plagiarism. Okay? There's really no tolerance on that because we're, that's dishonest. I don't like that. All right. Let's get into, we're going to wrap up the electricity chapter this morning and probably get into the optics of the eye. We have a 7th chapter, I think, 7th, the biological effects of nuclear radiation. Sometimes we get to that chapter and sometimes not. It's a short chapter. We might have time to get to it, but we're not going to have it. Huh? It's not really, but it's kind of fun. But we're definitely going to get optics of the eye. That's my favorite chapter, so I want to get into it. Because the eye is my favorite part of the body. Just next to the ear. The ear is probably my second favorite part of the body. Eye is phenomenal, what it does. So, let's see. Nervous system. Yeah, we had a flood. There's like 1.5 inches of water down this hallway. One of our water supplies upstairs, a fitting burst, and it leaked over the weekend and had about this much water. Huh?
Because it felt warmer in here, so I thought that was heaters.
No, those are they're just fans and dehumidifiers. All right. So the nervous system uses nerve cells to transmit information through the flow of electric charge. We'll talk about it in terms of current, actually, because remember, current is the flow of charges. There are a few purposes of the nervous system: sensory input, integration processes, and motor output. So the first is sensory input. This is sort of what we think of when we think of the nervous system. This is input from your surroundings. That is, external stimuli. And the other organ systems. And this is internal stimuli. And we'll call this the PNS, the peripheral nervous system. We'll define that in just a bit, I think. Yeah, we'll define that in just a second. This is the peripheral nervous system. PNS is the peripheral. in contrast to the central nervous system. Yeah.
When do you want us to give you back the books?
Oh, at the end of the semester.
Oh.
Exam 4.
We can bring them like that day.
Yeah. In fact, I won't post your grades until I get them back. Integration processes. This is the second purpose, or integration. This processes the sensory input. And determines what to do in response. This is mainly your brain. And that's going to be the central nervous system. So here C stands for central. So the peripheral nervous system and then the central nervous system. So I'll show you a picture here down below. And then finally, the third purpose is motor output. This is achieved by the peripheral nervous system. And it's just your nervous system causes the body to respond. All right, so I have a hot stove, put my hand on it. There is external stimuli. I have this sensory input, and that sends this to integration, sends that signal from my hand on the hot stove to my brain. The brain integrates all that stuff and causes a motor output, which of course is to pull my hand away. It's very, very fast. Like all this stuff goes on in a very short amount of time between the peripheral and the central nervous system. So two main parts, we sort of talked about this, the peripheral and the central nervous system. The central includes the brain and the spinal cord. And then the peripheral nervous system includes the nerves and everything else, basically, all the nerves throughout your body. The peripheral nervous system accomplishes the sensory input. It's like, you know, the hand on the hot stove. And then the central nervous system takes care of integration and sends information for motor output through the peripheral nervous system. PNS. All right, two main parts, peripheral and the central. Central is the brain, spinal cord. It does the process of integration. And then the peripheral nervous system responds to the central nervous system, both providing stimuli or input, sensory input through that external and internal stimuli. Internal stimuli would be like, I'm cold, I'm hot, or things aren't working right here. And then also motor output. All right. Make sure you know those two parts of the nervous system and know those three purposes. Sensory input, integration, and then output, motor output.
That was called the delivery system, the peripheral.
Okay.
Easier to remember.
Yeah, it delivers both input and output. Yeah, that's fine. But I want you to know it as a peripheral nervous system. There are two types of nerve tissue, the neuron and then the support cells. The neurons actually transmit an electrical signal. While the support cells are neuroglia. Provide various roles of support. They protect the neurons, such as the myelin sheath. I'll show you a picture, or we'll watch a video in just a bit. The myelin sheath. And those support cells, they do a variety of things, but they protect the neurons, they provide for the conduction of this electricity. We're concerned mainly with the neurons, so we won't talk much about the support cells, but you do need to know that they exist. They have these two types of nerve tissue. The neurons, which conduct electricity, they actually transmit this electrical charge in a similar way as, say, wires in a building, but in a different way too. They're quite different, but the result is the same, that we're moving charges from one spot to another. And then the support cells, they protect and sort of support the neurons. All right, but as I said, the main thing that we're looking at are the neurons. And the neurons consist of a cell body and with dendrites and axons. Oh no, well we won't get nearly as deep as you guys did. We'll just sort of do surface stuff. So this is our cell body, sort of center part. This is also called the soma. I think your book calls it that. I think it gives it that name. But the cell body is the main part of the neuron. It controls the flow of electric signals. Yep.
So, just to clarify, if the book cell body is called the soma.
The cell body is also called the soma. I think that your book uses that term as well. These are dendrites. Put or soma. These are our dendrites, these little tree-like structures. And the dendrite receives input signals and sends to the cell body. So this is just a single cell, right? A single nerve cell. It's going to be strung along a big thing. And it's going to send electrical signals all along its way. So we'll get electrical signals here that'll be coming into the neuron, and then they'll go to the cell body, and then the cell body will send an electrical signal along the length of the neuron. The axon is this thing. This transmits the signal and sends to the dendrites on the next neuron. All right, so the electrical signal comes in, says, oh no, the stove's hot. Sends it to the cell body, sends it along the axon, and then we'll send it on to the next neuron. Or maybe not, oh no, the stove's hot, but oh no, you better move your hand or you're going to burn yourself. The synapses are the end here, so these are the synapses. These are also the termination of the axon, right? The end of the axon. So these are also called the axon terminals. Just because that's the end of the axon, the terminus of the axon. And the synapses, they just are a connection between neurons. So they connect up, the synapses would connect up to the dendrites of the next neuron. And then that electrical signal would be processed through this web of neurons. Yeah, you need to know the different parts of the neuron. Absolutely. I'll give you a picture, kind of like I've done in the past. I'll ask you, what is the cell body? What is the axon? What are the dendrites? Absolutely. Oh, these are the myelin sheaths. Talked about that. Remember, those are support cells. The myelin sheaths are along the axon, sort of cover up the axon. You can think of them sort of as insulation if you want to think of them that way, like insulation on a copper wire. Although they work differently from the electricity that flows through copper wire. We'll talk about that. Let's watch this video. This is 2-Minute Neuroscience. You ever watch that YouTube channel? It's sort of like Minute Physics. You ever watch Minute Physics? No? Well, this is 2-Minute Neuroscience. I guess that neuroscience is just more complicated than physics, so they need 2 minutes instead of 1 minute. Let's see, where's YouTube?
Installment, I will discuss memory potential. Memory potential.
Remember what he said, we'll come back to that in a bit, but remember what he said about if the signal is strong enough, and he mentioned a couple words, action potential, and I think he also said membrane potential. Those are things that'll come back. And the potential is what we've been talking about, energy per unit charge. Remember, V is energy over charge, potential is energy over charge. That's what he's talking about. That if you get enough energy in this electrical signal, then it will send that signal on to the next neuron. We'll see that in a bit. So the neuron has lots of functions. Need to be aware of these and be able to identify them. The sensory neurons conduct input signals to the central nervous system. These are like our 5 senses. Remember, sensory input is one of the 3 main purposes of the nervous system, and that's achieved mainly by the peripheral nervous system. And the sensory neurons, they just take these input signals and they give them to the central nervous system. The motor neurons conduct the central nervous system to the effector organs. So these are still part of the peripheral nervous system, right? Because they're taking stuff from the central nervous system out to those, this is the motor output, that third function. They conduct these CNS signals to the effector organs. All right, mainly we're talking about muscles, right? Like, so if I touch a hot stove, it's my effector organs would be the muscles in my arm to pull my hand away. But they don't always have to be muscles. They can be your organs too. Your glands, organs. We talked about in the previous chapter one effect of this, that when your body temperature gets too cold, that your body will take on these involuntary actions to make you warm up. Shivering is an involuntary, and that's your muscles, but also just you'll release chemicals in your body to boost your BMR, your basal metabolic rate, which will cause your body to heat up. So those are our motor neurons, and then third, our interneurons is in between our sensory and motor neurons. So sort of an interplay between those two, interacting between our sensory and our motor neurons. Okay, so those are just 3 different classes of the neuron. Did you know the basic parts of the neuron? In that video, he talked about extra parts. You don't need to know those extra parts, just the ones that I listed. And then sort of the basics of how electricity flows through the neuron, from the dendrites to the cell body, along the axon, into the terminals, and then into the next neuron. And then these 3 different functions or classes of neurons. Parkinson's? I don't really know anything about Parkinson's. I believe you. Are you stating that or question? Yeah, I don't know. That'll make a good Parkinson's. To look at Parkinson's effect on the central nervous system. There could be some interesting stuff, I'm sure. All right. So electrical properties. Talk about electricity flowing in a neuron like it does in a wire. It's not exactly true. You get the same effect, that you get charges that will move from one point to another, but they do it in a different way. It's sort of this shuffle along the neuron. So electricity in a neuron doesn't move in the same way. So electricity doesn't move in a neuron in the same way as in a wire. Instead, ions move across the cell membrane. Perpendicular to the axon. So if you remember, let me do there's your dendrites, there's a cell body, and then you have the axon, and then you have your terminus. And so what you get is you get these ions that will move perpendicular across the cell membrane. All right, they don't move side to side, they move perpendicular to the axon. All right? And the motion of these ions causes the potential to change in the axon. So I have ions, cations or anions, that will move from one side to the other. When I get these shifting, I get this separation of charges across these, just like we did on a capacitor. Remember on a capacitor, when I separated the charges, it created a potential in between those two plates. So I can think about this as a capacitor. I imagine I have a capacitor here, and if I can separate the charges, where I get positive charges over here and negative charges over here, when I do that, what I do is I establish a potential between those two plates. So when I have these charges move back and forth across the cell potential in a particular way, and we'll talk about how they move, it creates a potential at that location in the axon. And this potential affects ions further down. So when I create this potential in this little section of the axon, what that does is it affects the next section of the axon in a similar way. If this potential is big enough, that is, I get a big enough separation of charges, like in a capacitor. If I get a big enough separation of charges with positive charges here and negative charges here, that creates a potential. Right? Because like a capacitor, when I separate the charges, I get a potential. And if I create a big enough potential, something we'll later call the action potential, it will cause a separation of charges here, and a separation of charges here, and then on down the line. So you see, when we talk about wires flow or charges flowing in a wire, it's a little simpler. That is, have an electron that will move along the wire. It moves actually in an electric field. But here it's a little bit different. I get the separation of charges that causes a potential, and then that affects a change in potential all the way down the axon. The electrical signal moves down the axon like a wave or like a pulse on a string or rope. You ever take a piece of rope and you just do like this? You know, do that, right? Or sometimes you might do it to exercise, or you just like send the rope. If you do a single pulse, that's kind of like the potential moving along the axon of a neuron. You have this pulse of potential, of an increase in potential that moves along the axon. And so it has the same effect of charges moving on a wire, that you're transmitting this electrical signal, but it just happens a little bit differently. Membrane potential is related to this. The axon has potassium cations, so that's going to be K plus, and anions of various types. So the K is for potassium. It's on our periodic table. What is it? Number 19 over there. It's our potassium cation. Remember, cation, you'll need to know this for the test. It's a positive ion. And anions of various types. Chlorine, just sort of various types of anions. Remember, anions, by the test, are negative ions. Remember, ions, you have a regular atom that has equal number of positive and negative charges. You create an ion by taking away an electrical charge. If I take away a negative charge, what does that produce? Positive, which is a cation. If I add an extra electrical charge, that's a what?
Oh, that's a negative.
That's a negative, so I have more electrons, and that's an anion.
It's the opposite of what you use.
Okay.
Oh, what's the
A is just for anion, or it's like it's not an element, it's just a generic sort of different types. There are actually more than just one type of anion involved. All right. These are separated by the cell membrane. From the sodium and chlorine ions. Chlorine is an anion on the outside of the axon. All right, so let's see. This is inside the axon. And this is outside the axon. Extracellular, intracellular, inside and outside of the nerve cell. And what I'm going to do is I'm going to have these ions shift back and forth. And what that does is that causes, like we said earlier, it causes us to have this separation of charges, where I have positive charges on one side and negative charges on the other side. That's really the big idea that I want you to take home from this, that if I separate these charges, it creates a potential, just like we saw with the capacitors. Remember that potential, Q is equal to CV, so V is equal to Q over C. We saw that. It's sort of like the Ohm's law for capacitors. That potential is given by the separation, the amount of charges that I separate between these two spaces. There are no metal plates here in the cell, but you still get extra charges here, and it has the same effect. Okay?
So, a capacitor has one positive and one negative.
Right, capacitor, we said we have two metal plates, right? Capacitor. I have charges on one side and charges on the other side. And even though this isn't really a capacitor, it works in the same way because I have a separation of charges. You need to know what a capacitor is for the test next week or in a couple of weeks. All right, so there are more potassium than sodium out than in. So by diffusion, diffusion just means that if I have ions in areas of high concentration, they'll move to an area of lower concentration. The sodium ions will move inside the axon, and the potassium ions move outside the axon. This is just by diffusion, because I have more in one place than I have in another place. So the sodium ions, which are over here, they'll move over here, just to sort of distribute so that they'll have equal numbers of sodium ions. It's not an electrical thing. It's just because I have all this extra sodium, it'll move over here. And because I have all this extra potassium, that'll move over here. And it'll get sort of spread out. What's that? Yeah. We call this a concentration gradient. Yeah, balance it out. And then, because of differing permeability in the cell membrane, for potassium and sodium cations, more potassium ions move out than sodium moves in. So I'm having this transfer of charges just because of our concentration gradients, right? Because I want to sort of separate, I want to have them all the same on both sides. But that cell membrane only lets certain ions through at a particular rate. It has a permeability. And that permeability is different for the potassium and the ion and the sodium. So I get more potassium and less sodium that's moving just because of the permeability. So the effect of that, because I have more potassiums moving out than sodiums moving in, is that the axon becomes negatively charged. Take a break here, let me show you. So this is the inside, right? This is inside the neuron. I got these potassiums moving to the left, and I got the sodiums moving to the right. But more potassiums are moving out than there are sodiums moving in. So that makes this side, what? Negative, because I've lost more potassiums than I've gained sodiums. And over here I get a positive. So I get negative over here and positive over here because I'm losing more potassiums than I'm gaining sodiums. All right, so this has a lower potential than the outside then, right? Because negative charges have a negative potential, so have a lower potential on the outside. And so there's a potential difference between the inside and the outside. It's called the membrane potential. Potential difference. I know this seems really complicated. Look back at the old test, you get a feel for what I'll ask. But I do want you to understand how these charges move back and forth, and I get this separation of charges. And that creates a potential difference on the in the neuron. So these sodium and potassium ions move in three ways, and we mentioned two of these. All right, and then there's a third that your book talks about. The sodium moves by a chemical gradient. That means that sodium's moving out. Potassium's moving out. Sodium's moving in. There are other things, but these are the big players. All right? They're the ones that affect the electric potential of the cell the most. Chemical gradient. There's also an electrical gradient. Which is going to have our potassiums in and our sodiums out. And then there's something else. Your book talks about this. You sort of need to know it in name only. Is the sodium-potassium pump. We can call it the sodium-potassium pump. And this moves potassiums in and sodiums out of the cell. In is into the cell, out is out of the cell. If you've had anatomy, you've talked about the sodium-potassium pump, I'm sure. Your book talks about it in greater detail. I just want you to know that it's one of the ways that charges move around. We'll watch a video. They describe it in more detail. Let's fill in this. I'll show you that. So the net result is that the inside of the cell is slightly negative. So more negative charges than positive charges. And that gives it a resting potential. There are three membrane potentials. We'll talk about resting and action potentials. So resting is an important word. It's not just, it's an actual potential. And that potential is about minus 70 millivolts. Yeah. I'll show you a graph where I have this resting potential. Membrane potential, that is the potential across the cell membrane. And that membrane potential can change. When it's just doing nothing, it's about minus 70 millivolts. But it changes when the neuron is active. Let's watch this.
Answer this question.
All right. You don't really need to know about the sodium potassium pump, but it is an important part of the cell, of the neuron, in keeping and then sort of establishing what the potential is inside of it. You need to know about that resting potential, that it's that minus 70 millivolts. There's another type of potential, and this is when the neuron is activated. So when you have some input or when you have some output, when it's actually communicating information. And the action potential occurs when the membrane potential exceeds the threshold potential. So the action potential occurs when when a stimulus occurs in the neuron. So under stimulation, the cell membrane will allow ions to move across, and then this changes the membrane potential. Just say again, the membrane potential is just what is the potential across the cell membrane? What is the potential between the inside and the outside of the neuron? And the action potential is a specific type of membrane potential, and it has a particular value. The resting potential, similarly, is when the membrane potential has a particular value, that minus 70 millivolts. We can have two situations. We can have graded potentials and action potentials. And action potentials, this is when the stimulus is strong enough, so like the hot stove. The membrane allows the passage of ions so that the membrane potential increases. It goes from minus 70 millivolts to about plus 30 millivolts. And this graph shows the resting potential here. Your cell is just at minus 70 millivolts. And then something happens. Pinch yourself, put your hand on hot stove, whatever, and that creates some stimulus that's sent out into your body. And when the stimulus is strong enough, when it's a big enough field to your body, the ions are allowed to pass back and forth between the membrane, and that causes an increase of your potential. That's called your action potential when it goes up to about 30 millivolts. Ions are allowed to pass through the membrane, and a small region of the axon changes potential. And we talked about this. I have my axon. This is my axon right here. I have the separations of charges, say plus, minus, so I get a V right there, and this sort of ripples effect all the way down the length of the axon. I get an increase in potential at one point on the axon that causes an exchange of ions in the next section, and the next section, and the next section. When you talk about it, it sounds like a long thing, but it happens very, very quickly. This goes on to the adjacent region, like a pulse on a string, causing a similar effect. And this current, not really a current, but it's a lot like a current, moves parallel to the membrane along the axon. Action potentials, that's what this is called. Occur with the membrane potential, or excuse me, this should be when the membrane potential exceeds the threshold potential. The threshold is about minus 50 millivolts. However, when the stimulus is less, a graded potential occurs. Let's go back to that threshold potential. I'll show you on the graph. Forget about graded potential right now. I want to go back and show you on that graph. So if you have a strong stimulus, that's applied, either internal stimuli or external stimuli, it causes those ions to exchange between the cell membrane, and it causes your resting potential to increase. And if it increases enough, if it increases up to about minus 55 millivolts, you get enough separation of charges to increase your potential, your membrane potential, to about minus 55. This is called our threshold potential. And we get to that, it's like the thing just goes off. Then we get this increase in the exchange of ions, and so our voltage will rise. This is called the action potential right here. So this is our resting potential. This, the dashed line, is our threshold potential. In order to have an action potential, you have to reach this threshold. And then once you reach that threshold, that sort of sets off this onslaught of charge transferal across the cell membrane. And then I get a further increase. But if I don't reach that threshold potential, if I don't reach this minus 55 millivolts, then I don't get this. This doesn't occur. This big increase, this action potential. I like to give this graph on tests. I often have. And I'll ask you certain things like, what is this? This is your resting potential. What is this, minus 55? That's your threshold. What does this plus 30 right here represent? That's our action potential. So you really have three different potentials: resting, threshold, and action potential. These are really fast acting. It's a strong stimuli like the hand on the stove, something where your body is required to respond very, very quickly. And so this occurs very, very quickly. However, we have other stimuli that we don't really need to respond to, like I just brush up against somebody in the hallway. That's not an alarming thing, and you don't respond very quickly to that. When that happens, the stimulus isn't as strong, you don't get up to the minus 55. And when you have that, you don't get an action potential, you get a what? No, you get the graded potential. So we have two types of actions. We have the action potential and then the graded potential. And that happens a lot more slowly. We're not going to get into graded potentials, but they just propagate more slowly along the axon. So your neurons can act fast, right, when you need to, but they can also act more slowly when you don't need to. along the axon. And this would be, you know, less critical stimuli. It's really fascinating, the nervous system. It's immensely complicated. Right? It's faster than really anything that we have that we can make. But it also can process a lot of information all at once. Okay? Cool, no? Like I said, brushing up against somebody in the hallway would be a graded potential. And it allows that charge to go across the axon, but in a much slower way. I have one more video we'll watch, and then we'll do some clicker questions. Now let's try some of these questions. We'll try this one. Which of these parts of the body has a higher resistance? Yeah, this might not be immediately intuitive. It talks about this in your book, but we'll stop here at 28. B is right here. The dry skin has a higher resistance than inside the body. In a neuron, the potential inside the cell is usually what? Positive, negative, zero, or neutral? All right, let's stop at 30. Negative, right. So remember, that's the resting potential. In a neuron, the potential is usually negative. That's our resting potential. It's only when it's being utilized in some way to send some input or output does it go above that. What this is. So have a strong stimulus, the neurons experience a what that causes them to act. All right, 27, I'll stop. Okay, awesome. A is right. The action potential. Remember that action potential is equal to about, well, never mind. It occurs when you reach about a minus 55 millivolts, when you go from minus 70 to minus 55, and then that kicks in the action potential. The action potential actually goes up to about 30 millivolts, positive 30. We're not going to do this. We didn't talk about this. I'll mention it to you just because it's interesting. The in-body, remember I showed you the results from the in-body? They have one over in the rec center. The thing you stand on, and it sends an electrical current to you, and it analyzes your body composition, the amount of water mass, the amount of muscle mass, the amount of bone mass. The way that it's able to do that is it sends electrical signals to your body of different frequencies. And when it has different frequencies, it's able to sample your body in different ways. So it can sample your arms and your torso and your organs on the inside. It's just it's multiple frequencies, and that allows you to sample those different body parts. Yeah, D. Yeah, D. D would be the right answer. The E meter. We talked about this last time before the break. What does the E meter do? Remember that was the thing that Scientologists use? You hold those two metal cans. What does it measure? Does it measure a current, a resistance, a voltage, or an electric field of the human body? All right, 37, I'll stop. Resistance is right. It uses those other things, but it's measuring resistance. So remember the E-meter, what it does is you hold these metal cans, and they're connected to a battery. That's a symbol for a battery. And they send a current through the wire, which goes across your arms and into the next, so that you create a circuit. And it does create a current and with a voltage, but what you're doing is you're measuring the resistance. So as you hold those metal cans, it measures your resistance always, and then when you answer questions, like it's sort of like a lie detector, right? If you answer the questions incorrectly, or if the questions just make you feel uncomfortable, the resistance of your body changes a little bit. Your palms might get sweaty. The inside of your body changes. Your heart might race, and that affects the resistance. And then they use that to read it to see, how you're responding to those questions. It's kind of cool. I mean, I don't agree with how they use it, but it's still kind of cool. And which of these purposes of the nervous system? Remember the purposes of the nervous system? All right, let's stop at 28. Okay, good. A is right. You might have thought vision was one. I understand why you would think vision is a purpose of the nervous system, because really the nervous system is involved in vision. But remember that vision is really a sensory input. So the three purposes are sensory input, integration, and motor output. So A is the right answer. Alrighty? Why can you never hear pterodactyls go to the bathroom? Because the P is silent. Good 5th grade joke for you. Oh, that's the end of chapter 5. All right. So chapter 5, there was quite a bit in chapter 5. We talked about potentials, current, resistance, and capacitance. A little bit about some basic circuits. Our fields, potentials, and potential energy. All right. Read through the chapters, look at the old tests, and read through your notes. That's how I make out the test. I look at the chapter. I don't pick out stuff that we didn't cover in class for the test, but it's still a good way for you to review the material. Look at the old test and look at your notes. Alrighty? It's one of our tougher chapters. We have some difficult content, so if you're not up on it, I would start preparing for that now. We have a good long while to the test, since we have it on the final day. You have plenty of time to study. But I find that often means that doesn't mean that they're more prepared. It might even mean that they're less prepared because they sort of put it off. Don't do that, okay? Be preparing now. Even just 20 or 30 minutes a day will help you. Read it at bedtime. If you have kids, you can read it to your kids at bedtime. Even better, right? All right. So optics of the eye. We're going to see some things that we've already seen because we did waves with sound, and so we'll have similar things here because light is a wave. Light is an electromagnetic wave. We say electromagnetic because it's a changing electric field and it's a changing magnetic field. And we're not going to get into the details of it, but it acts very much like a wave, where the electric field is one value and then it's another value, and it travels through space like a wave. So light consists of these electromagnetic waves, EM waves, EM, where the electric and magnetic fields oscillate back and forth. They're different from other waves because we're dealing with electric and magnetic fields. They don't need a medium to travel through. Whereas when we're dealing with other waves like pressure waves, transverse, longitudinal waves, those needed a medium, but these don't need a medium, which is a good thing because through the darkness and vastness of space, light wouldn't be able to reach us. So we wouldn't see the stars at night, we wouldn't see the sun during the day if it required a medium. These EM waves are caused by moving electrons. These EM waves are caused by moving electrons. It's kind of cool. In fact, if you ever dealt with any radio antenna, any shortwave radio operators, people don't really do that anymore, do. It's just like old men that do shortwave radio. But with shortwave radio, you have an antenna. It's just a metal rod that sticks up in the sky. So this is our antenna. And what you have is you have electrons that move back and forth, back and forth. And what they do is they change the electric field and the magnetic field as they move back and forth, and will create this electromagnetic wave. So as these electrons are moving back and forth, they create a wave that then travels through space. And depending on how fast those electrons move back and forth, it will change the frequency or the wavelength of that wave. And you can do that simply, I say fairly simply, just with electrical circuits that will change how quickly those electrons move back and forth. So moving electrons generate electromagnetic waves. Let's see, I don't know what this animation, I forget what the animation is. Let me look it up.
Okay, so this might be a dumb question, but is that how Wi-Fi works?
Yeah, it's a similar thing. Oh yeah, here we go. This was the animation I was thinking about. Yeah, so this is an animation of an antenna. You have these charges moving back and forth. This is a switching dipole. So a dipole is a positive and a negative. And so here, notice this becomes positive, negative, positive, negative, positive, negative. And likewise, the electrons and the protons are switching directions. That basically just means that the electrons are moving back and forth. So when the electrons move down here, it's positive up here. Because protons don't really move around. It's really just the electrons. But what that does is it creates this electric or magnetic field that then propagates out into space. That's a simple one, but if you're sending more complicated signals, then you make your electrons move in more complicated ways. EM waves have all the other same properties of waves, have the same wave properties as other waves. So everything that we did in the sound chapter will still hold for this chapter. We have a speed, we have a wavelength, a frequency, and just to remind you, these things are on your equation sheet, but just to remind you that the velocity, the speed of a wave is equal to the wavelength times the frequency. The frequency is equal to 1 over the period, and so the speed is also wavelength over a period. And remember, on a wave, if this is a history graph, that means that I'm looking at time versus displacement or amplitude. This is our period, t, 1t. This is our amplitude. And if I'm looking at a snapshot graph where this is not time, but this is an XY position, then this was also our wavelength. We talked about snapshot and history graphs back in our sound chapter. Have we had an exam on that chapter yet? Do you recall? I don't remember. That was on our last exam. Okay.
Yeah.
Well, you can see some other stuff. It'll be in the context of electromagnetic waves. But we'll talk about this, the speed of a wave, soon. All. What's that? With the what? I? Oh, okay. Well, this is the eye. This is on
I like the no. The eye.
the ear.
Yeah, that thing.
Sound chapter, yes.
Sound chapter.
All electromagnetic waves travel at the same speed in a vacuum. They say that, and that speed we call c, it's equal to 3 times 10 to the 8th meters per second. It takes about 8 seconds for light to get from the sun to the earth. Is that right? 8 seconds? 8 minutes?
Yeah, that's 8 minutes.
Okay, minute. It takes a not zero amount of time for light to get from the sun to the earth, because it travels at a finite speed. We'll see that light, electromagnetic waves, can travel at slower speeds, but they can't travel faster. So they can travel slower, but not faster. Than that value, than C. We'll see that it travels slower when it goes into other media. Like, for example, when light travels from a vacuum into, say, a piece of glass, then it's going to slow down. And that'll cause a phenomenon that we'll call refraction, or the bending of light.
So is this the eye chapter?
This is the eye and light, both. The eye is used to process light, so. All right?
So you can travel like what?
Oh, it can travel slower than that speed, but not faster. It's the electromagnetic spectrum. You need to know the basics of the electromagnetic spectrum. Basically, these things right here. I want you to know the order of energy and wavelength. So, gamma rays are the highest energy, and they're also the highest frequency, but they're the shortest wavelength. Remember, frequency and wavelength are inversely related. So if I have a short wavelength, a very small wavelength, I have a very high frequency. And the frequency is by this graph right here. You can see the frequency and the wavelength are depicted by this sort of wave. Go gamma rays to X-rays to ultraviolet. And then I have the visible part of the spectrum. This is the high energy part of the visible part. Right, that's the sort of the violet end, all the way down to the red. You know the mnemonic for this, for the order of the colors? What is it, Jonah? Roy G. Biv. Although in this case it's backwards, so it's Roy. Roy G. Biv. And then beyond that, you have infrared, microwave, and radio. All right? Wavelength is small, wavelength is big, frequency is big, frequency is small. Energy is big, energy is small. I want you to know the order of those. There are some other parts within this, but these are really the only ones that you need to know. Radio can be really long wavelengths. These can be kilometer-sized wavelengths, kilometer-sized waves. And those can actually go around the Earth. So those shortwave radios, they use very long wavelength radio waves, or electromagnetic waves, that can travel, they can actually bounce off the atmosphere and travel all the way around the Earth. All right, so you can have waves that will be as big as planets. You can have, this planet Earth right here, you can have a wave that will travel around the Earth like that. A radio wave. The energy of a wave is given by the frequency. This will help you to remember how the energy is related. It's equal to h times f. H is Planck's constant. You don't need to know the value of this, but I'm going to give it to you.
6.626 times.
Oh, come on. Yeah, you're right. I rounded off. Or negative 34.
Oh, that's not 26.
It's 34. I forget the units for it.
Yeah, 23 is Avogadro.
Right, that's Avogadro's number. Okay, Planck's constant. Really what's important here is I want you to recognize the dependence of energy on frequency. H is just a constant. Don't really worry about it. But you might have heard about this in the news. Have y'all heard about the new mass standard for the kilogram? We talked about at the beginning of the semester about mass standards and how in a global scientific community that you need to have agreed upon standards of measure. And they better be really accurate too, because we measure things that require great accuracy. In time, for example, with GPS and cellular technology, you need to have a very good knowledge of what the time is. You need to measure times very, very accurately. And that's why we use the cesium atom for our time standard, because the cesium atom has a very well-known frequency that's known very well, or a very well-known frequency that's very accurate and can measure small amounts of time very easily. Do y'all remember what the standard for the kilogram was? No, that was the standard for the meter, but close.
It's a cylinder of platinum and iridium.
Right. The standard for the meter used to be a bar in France, but now we define it based on the speed of light. So time is based on the frequency of a cesium atom. That's just a physical constant. The meter is based on the speed of light. And for a long, long time, the kilogram was based on a cylinder, a physical artifact that was in France at the Standards of Measurement, or the Institute of Standards of. It's in France, all right? I think it's French.
Everything's in France.
The name of the lab, yeah. And so that's a problem because a kilogram, just this little thing, is not very accurate. One, the mass of that kilogram is changing, and then it's also just difficult to measure very small quantities accurately. And so for many years, people have been trying to change the standard, and last week they did. They changed it to a standard that's based on this constant, the 6.63 times 10 to the minus 34, the Planck's constant. They did it with something called a watt balance. Did we watch that video?
Mm-hmm.
About the watt balance? Yeah, they decided to go with that. There were two competing options. One was a silicon sphere. They made the sphere out of silicon, and they said, okay, this is our kilogram, and then they counted the number of atoms in it. And so the standard for the kilogram was a number of atoms of this particular isotope of silicon. And so it was based on the mass of a silicon atom. That's physical.
That was gonna do the same thing as the other thing? Yeah, exactly.
Well, no, because it wasn't a sphere. That wasn't the standard. The standard, they just created this sphere, and then they counted the number of atoms in it. And then the sphere you just get rid of. And then the standard would have been the number of atoms. So it's just this number of silicon atoms. That didn't win. They decided that wasn't it. So what they did instead is they used a watt balance. And a watt balance is a particular type of scale. You can measure the mass of things. And they measured the mass of the big K of that platinum iridium cylinder, and they converted that into a current. That's what the watt balance does. But in the end, they were basing it on this Planck's constant. So now all of our standards of measurement are based on physical constants. That's good news for you and me. It means our cell phones are going to work. It means that our computers are going to work right. It means that all the cool stuff that we do will function. So you can rest easy at night, I think, knowing that the new standard is based on a physical constant.
So, what's the arrow?
The arrow? Oh, that E is proportional to F. All right, let's try a few of these clicker questions. If you want, you can do these color sheet a little bit later. We're not going to do it here. Light is a what with both what and what? Alright, we'll stop at 32. 32. Look at y'all. You're awesome. It is a wave with both frequency and wavelength. Which of these has the highest energy? Blue light, ultraviolet light, radio waves, or gamma rays? All right, let's stop at 22. Awesome. D is right. Gamma rays. Do these last two before we leave. What's the proper order of these from smallest to biggest energy? So pick the one with the smallest energy and then go to the biggest. We already know that gamma rays has the biggest, so it has to be one of those. You just need to know which one has the smallest. All right, just a few more seconds. Awesome. Good. B is right. Microwaves, infrared, ultraviolet, and gamma rays. Let's do this last one in the last few seconds. What's the energy dependent upon? All right, just a few more seconds. 18, I'll stop. All right, D is right. Frequency. Alrighty, y'all have a good day. Yeah, knock knock. Knock knock. Smell mop. Oh, no thanks. I'll leave that with y'all. That's another 5th grade joke. Alright. Huh?
You have 3 more touch-up ones.
Yeah.
You can take them, around Thursday. Oh,